Hi, I'm Ben-Yaakov. This presentation is entitled AC Analysis of Small Signal in SPICE, including, of course, LTspice. I've been requested by a number of people watching my YouTube channel to cover this subject, which seems that for some seem to be very confusing. Now, I'm assuming here a basic working knowledge of LTspice, that is how to start a simulation, how to do the plotting and drawing, etc. I'm not going to cover that, only the question of AC analysis. Let me start with some background. The SPICE simulator was developed at the Electronic Research Laboratory of the University of California at Berkeley around 1973 by Lawrence Nagel, and with the direction of his advisor, Professor Donald Pedersen. Now, since it was supported by a grant from the US federal government, the program was made public domain. So, since its introduction, the core of SPICE, that is the actual simulation engine, was adopted for free in different ways by many companies, including LTspice, which is used for demonstration in this presentation. Now, since the core is the same, then therefore AC analysis is the same in all SPICE-based simulator. Okay, so although I'm showing it for LTspice, it will be equally correct for, say, PSpice or some other simulator. Now, the basic simulation types of SPICE include DC sweep analysis. This is a sequence of operating point solution. That is, there is some source which is sweeping, the voltage is changing, say if it's a voltage source, and for each point the operating point is calculated and then can be drawn. So this is a DC sweep. Transient is a solution as a function of time, and this will be can be drawn then as a function of time, like voltage developing or a transient or whatever. Now, AC analysis, which is also called small signal analysis, is what we are going to discuss in this presentation. So, as I'll later on discuss in more detail, let me just summarize here at the beginning that the basic AC analysis is a frequency domain phasor analysis, that is J omega, etc., as we are used to do calculation of AC circuits, linear circuits, and it is solving for voltages and currents by Kirchhoff's law. For a range of frequency, you define the range and it will solve it for each frequency within this range, or a number of points within this range. It is applicable, being a phasor calculation, only to linear circuits, and we'll talk about it a lot later on, or to nonlinear circuits after linearization. And some of this linearization is done automatically by SPICE. It's transparent to the user, and I'll of course talk about it a little bit later in more detail. So let's start off with something simple. Suppose I like to get a transfer function between the input and output of this low-pass filter, R and C. And so I want V out over V in as a function of frequency. I want something like this. So what happens at SPICE, it will sort of replace the capacitor by 1 over J 2 pi F 10 to the minus 6, 1 microfarad. And then for the range that I've specified, the number of points that I've specified, it will calculate the transfer function in a phasor way between input and output, and then plot these here, if I want the ratio or just the output, as a function of the frequency. So this is very basic AC analysis. Now, the way to do it in LTspice or in SPICE in general is you need to have a source which is specified for AC analysis. In LTspice, it's the same source, only that you define it as AC. Here it is. Okay, it could be pulse, it could be sinusoidal, it could be exponential. So for AC analysis, you have to define it as an AC source. Okay, and you have to define the amplitude. You have to set the amplitude. And here it's 1 volt, okay? So this is the way it is done in SPICE, the circuit. And then you have to choose the range between starting frequency of 10 to, say, 1 megahertz. And then you have to specify the type of the switch. It could be decade, could be linear. Decade is usually more convenient. If you like a large span of frequencies, then a decade scale is nice. And then the number of points, say 100 is okay. You can have it more for the resolution that you want. And then you hit the simulation icon, and it'll run. And then you can plot, say, the output voltage as a function of frequency. This will be the amplitude. This will be the phase. Now, since the input voltage is 1 volt, then V out is actually the actual value. Now, this is now in dB, but you can change it to a linear scale if you wish. Usually dB is for transfer function a better way to look at it. You can do it logarithmically or by a linear scale. We'll see it later on. Now, what happens if you set the AC voltage to be, say, 1000 volt, 1 kilovolt? Okay, this is this voltage here is now 1 kilovolt. Now this is a linear circuit. Really doesn't matter. Nothing will burn here. Nothing will get warm or explode. It is just a calculation, a mathematical calculation. What will happen is that the current will be 1,000 times larger. That's what will happen. And what is important, the ratio between output and input will be the same, okay? So a linear circuit is insensitive to the amplitude. Very, very important to remember that, because this is a source of confusion later on. We'll talk about it. So here it is. If it is 1000, then we get here 60 dB. It's in dB, 10 to the third. And of course, if in a linear scale, it's 1 kilovolt. Now, if I divide the V out to 1 kilovolt, which is the input, it's not 1 now, it's 1000, then I'll get the same thing here, okay? So the point is, again, that for AC analysis, you can use any amplitude you wish. Very convenient to use 1, because then you don't have to divide in anything by anything, because it's just one unity signal. Now, what about DC? If you have DC in the circuit, here I've added DC to this AC, phasor analysis does not include DC. So the simulator by itself will eliminate this thing. A voltage will become a short, a voltage source, a current source will become an open circuit, and then it will run it without it, okay? So the DC is eliminated. It's not included in the phasor analysis. Now, what happens if you run an AC simulation on a circuit that includes a non-linear element? For example, a diode, okay? Now, the first thing to be done by SPICE or LTspice would be to find the operating point, okay, of the circuit. And then it'll take the local derivative around this operating point. And in the case of the diode, say, if this is the curve of VI, should be V here. In this case, we are getting the local inductance, GAC, small signal inductance, or 1 over it would be like RAC. So now SPICE is referring to this element as replacing the diode in the AC analysis. So if I have a diode, SPICE has this template built in, okay? This is the equation of the current of the diode. This is the voltage here, VD. It's shown as a current source or dependent current source. It has also a capacitor which is voltage dependent. This is the dependency. So once you are at a given operating point, what SPICE will do before running an AC analysis, it will calculate this derivative here, okay, to get the resistance. Now, obviously, SPICE, being a program, cannot do it analytically. What it's doing, the calculation will be in a numerical way. That is, it will take VD and then add to it some delta V. It'll get the I plus delta I, and then it'll divide the delta V by delta I to get the RD. Okay? So it is done numerically, and it is generating this equivalent circuit. RS is just the contact resistance of the diode. So when you have a circuit like this, and you run an AC analysis, this is eliminated in the analysis, but it is used to find the operating point. And at the operating point, it will extract the small signal model or equivalent circuit for the diode, and then it will run a phasor analysis. And here is, for example, V out, in this case, for say 3 volt bias. We are pretty high on the curve of the diode, and again AC analysis. Now, what will happen if I'll put here a higher voltage, like 1 kilovolt? Nothing. I mean, it'll be the same thing, except that the magnitude here will be 1,000 times larger, and the current will be 1,000 times larger, because it's a linear circuit after linearization. Very important. Now, if I change the DC, it was here 3 and now it is 0.1. Obviously, I'm lower on the curve. The resistance is higher, and I can see it here. The voltage is high. You see here it's attenuated because it's a low RAC resistance, and here the resistance is higher. And also the breakpoint is moving to a lower frequency because also the capacitance is becoming larger. Okay, so this is done automatically. Now, in SPICE, we have different models. There is a model which is a genuine model, and this model will be such that it will be compatible with DC sweep analysis, transient analysis, and AC analysis. This is a real SPICE model, a genuine model. But not all the models will support all these analyses. We'll talk about it later. Now, some models are already built in. For example, diodes, BJT transistor, MOSFETs, and other are already built in SPICE. In fact, they were built in Berkeley SPICE, 1974, 73. And the difference between different diodes and BJT transistors is just in the parameters. It's not in the model. The model is the same. MOSFET have a different model, I'm sorry. MOSFET have a number of models, but BJT is the same, and also for the diode. Okay? So, SPICE has the procedure to handle these, because the equations of the diode and the equation for the transistors are already built in, and it can do the equivalent circuit. The template for the equivalent circuit is already there, so it goes automatically. It's doing it automatically, transparent to the user. However, there are other models of more complicated circuitry, for example, operational amplifier, and they are built as a sub-circuit, meaning that you have a number of resistor, capacitor, dependent source, etc., maybe transistors inside. You don't have the whole transistors of an operational amplifier. This is just too heavy. There is an equivalent circuit which sort of mimics the operation of the operational amplifier. Now, also, you can have a DC-DC converter, and you can have some other units, and there are libraries. LTspice has the library with many different units. We'll see it a little bit later. So here is an example. Here is a operational amplifier from the library, and I'm running now a transient analysis. This is a time domain analysis, okay? Which I'm just showing it as a reference here. So I have a amplifier that I took out of the library. I've to power supply. It's a plus minus supply. I have here a source which is a time domain source, and I have the amplifier and a feedback. Forget about this for a minute. And of course, it's like a follower or times 2 non-inverting amplifier. Okay, it's a times 2. Now, I'm feeding here a sinusoidal waveform here, and this is the red one, and the output will be twice, and here is the output, 2 volt, 1 volt input, 2 volt output, and this is the frequency. Everything is fine. Okay. Now this model is compatible with also AC analysis, so I can run also AC analysis on it. Okay, so to run a given analysis, you have to activate the analysis. So for the transient, this is activated, and the blue one is actually put on hold. This is not looked at, and there is a procedure to release it. So I can make this one blue and this one black. Here it is. So now I will be running AC analysis. I've put AC 100 volt, and here is the output. Now, again, although this is an operational amplifier, if it is compatible with AC analysis, SPICE will linearize it, make out of it an equivalent circuit which is linear and therefore insensitive to the amplitude, and this is just for demonstration. I put here a 100 volt, nothing will happen to the amplifier, it will not burn out, everything is fine because it's an equivalent circuit which has nothing to do with the actual circuit. And then while I am running it, I'll get this value, and if I take V out over V in, this is what I'm getting, and I'll get the same thing if this would be 1. Okay, they'll be the same thing because again it is a linear circuit. Now, once I'm running here an AC analysis, I can look at some other signals. For example, very nicely, I can see what is the open loop gain of this amplifier, because I have access to these 2 points. This is the input. Now, measuring the input and then to get the gain is very tricky, because as you touch this point, it's going to be very noisy, but in simulation there is no problem. So if I run this as I ran it before, and just look at the ratio between this voltage and the voltage between these 2 points, which is these two, I'm getting the open loop gain of the amplifier. Very, very nice. At low frequency, it's about 100 dB, and then the crossover frequency is here. I see like 2 megahertz, and here I see the phase at the end of the bandwidth. Very, very, very nice. I can do other things with AC analysis. For example, I can examine the circuit to see how it behaves in terms of the stability, etc. Just for demonstration, I've put here a capacitor. This is a problem because due to this capacitor, there is a phase lag here. The amplifier itself has a phase lag, so it's bound to oscillate, to be unstable here. Now, if I run just an AC analysis, this is just an AC analysis, as I did before, I see the behavior that indeed the amplitude is increasing, the gain is increasing at higher frequency, because this becomes a low impedance, and therefore the gain is becoming larger and larger. But there is some funny thing here, and to examine this, I'd like to look at the loop gain of this circuit. Okay? To do this, I can activate this AC source, which was 0 up to now. I'll make this source 0. Okay? Here this is 0. Now, as we know, and you can find the videos in my YouTube channel, which is explaining it in detail, by having this source here, I can get the loop gain as the ratio between this voltage and this voltage around this excitation. Okay? Because I have an excitation here, so I have a signal coming in, here, all the way coming out, so therefore this signal divided by this is the loop gain. This is exactly how we measure loop gain by network analyzer. Okay, there is an injector which is put like here, or usually it will be a small resistor on which we impose a voltage, which is like a voltage source, and this is what we do. So if I do that, here is what I got. You see, this is the loop gain, this is the phase, and here at 0 dB, I see 0 phase. Now, this is now the real phase. It's not like usually we add or subtract 180 degree because of 1 plus beta A, etc. Here, we are not doing that. We just look at the phase as is, and 0 means positive feedback. That's what it means, okay? In the conventional, it would be like minus 180 degrees. And we see that at 0 dB, you have 0 phase, so it's a positive feedback. And the reason, as I have said, there is a phase lag here of about 90 degrees at high frequency. There is a phase lag here, and the amplifier itself, let's have a look at the amplifier. Here's the amplifier. This is the phase of the amplifier, 90 degree. And therefore, it's has a phase margin of 0. And to test this, what I did here, now I've converted this source to be a step. It's a pulse of 1 volt. Here it is. And you see, I'll give it here a step, it starts to oscillate, okay? So, there's a lot you can do with AC analysis if indeed the element that you are now simulating is compatible with AC analysis. Not all models are compatible with AC analysis. And here is another example. For example, if I like to look at the output impedance, output resistance of an amplifier, open loop, okay? Now, you cannot run simulation open loop similarly that you cannot run measurements in open loop because the gain is very high of operational amplifier. There is noise, and whatever you do, you have to trim it very carefully. So the best thing to do is to close the loop, and here it is closed. It's in a follower here, okay? There is a resistor here, that's it, it's a follower. But I've put here a very, very large capacitor so that it's 100 farad. In simulation I can do that. So that in the frequency of range of interest, this will be like a short, so there is no feedback. So therefore, this amplifier looks like open loop at these frequencies where this impedance is very, very small as compared to the 10 mega ohm. Okay? So now I've put a current source, AC current source, for the AC analysis. 1 amp. Don't worry. Nothing will happen to the amplifier. It will not be burned out. It will not go into saturation because this is AC analysis on the linearized amplifier. And it could be 1 milliamp, could be 1 microamp. It will be the same thing except that the scaling will be according to the magnitude of the current. And conveniently, I put it 1 amp, so the voltage here will be the impedance. Now I put here just for loading a little bit 100 kilo ohm. So when running it, I know I have 100 kilo ohm, and then there's a 10 mega ohm, which is also large, of course. But I haven't mentioned it earlier, and I should stress that it is extremely important before running an AC analysis to make sure that the operating point is the one that you wish to have. This is very important in nonlinear circuits because the procedure that SPICE is going through is finding operating point, linearizing the circuit around the operating point, and then running the AC analysis. Now, if the operating point is incorrect, you'll get incorrect answers. So how can you tell? There is this directive dot operating point that you can run independent of any analysis by itself. Once you do this, that is, you have to operate it, make it in black. And when you run it, here is what you get. And you see that I get, this is the 5 volt, and this is the output 2.5, and let's have a look here. This is 2.5, so the output indeed should be 2.5, okay, and it is. And I can actually look at this point too. Minus is also 2.5, so I know that I am in the proper operating point. Very, very important to look at the operating point before running AC analysis if you have a nonlinear circuit. So I have the right operating point, I'm running it, and I'm looking at the voltage here. Here it is, and this is what I'm getting. I'm getting that the output impedance of this model of the amplifier, this is the model, it's a simulation model, that's not the amplifier itself, okay? So within the accuracy of the model, we get it to be about 200 ohms, okay? Here is the effect of this capacitor at very, very low frequencies. It is still higher impedance, and only at 100 millihertz, 0.1 hertz, you can consider it as like a short. So disregard this beginning here, and so this is it. And as you can see, in this case, it shows that it is independent on the frequency. This does not make too much sense because there are some always parasitic capacitances. You expect it to be a bit in the real amplifier to be a bit frequency dependent, but that's what the model is showing. Now what about PWM converters or some other complex units? You have in, say, LTspice, you have the units, the model of the converter, and in fact they have this the so-called jig, or the whole circuit, a demo circuit that you can get out and run it. It will run very nicely in the proper analysis, but this is not compatible with AC analysis. You cannot run it in AC analysis. I mean, you can run it, but it'll give you some nonsense, okay? So, what can you do? Well, for that, you can use behavioral average simulation, and this is something that I've been working on for many years, and you can find in my YouTube channel many videos on this subject, how to model in a behavioral way. We'll talk about behavioral modeling in a minute, but how to model the unit PWM converter, switch mode converter. There is another way which is more tedious, and you can actually have a script written that will do it for you in LTspice, and this is injecting a series of sinusoidal signals at various frequencies, and then looking at the input and output, collecting this data and plotting it. This is very tedious, but you can do that. Some other simulators actually do AC analysis in this way. This is not the way of SPICE. SPICE is doing phasor simulation, okay? Some other simulators don't have AC, like PSIM does not have AC, but you can still do this simulation by injection of a series of sinusoidal signals at the range of frequency that you are interested in. So let's talk a little bit about behavioral models, which are very important. Now, suppose I have a circuit like this, we talked about it. Now I'm running the large signal. This is transient analysis. This is a sinusoidal waveform. It has a DC of 3 volt. The amplitude is 10, so it's a shifted sinusoidal waveform. Now, obviously, this diode will sometimes be in conduction, sometimes it will be blocked. Now, suppose I like to find what is the power dissipation of this diode. By the way, LTspice has a feature that you can, by clicking, look at this value, but I'm not talking about that. I'm talking about how can you do it yourself, okay? So what is power? Power is current times voltage. So now you can invoke this behavioral source. A behavioral source, a voltage behavioral source, means that you can write here any equation that you want, which could be a constant, of course, or a function of variables which are obtained during simulation. Now, during simulation, at each particular point, at particular time, this is transient analysis, You get a value for the current, you get a value for the voltage. This is the output here will be the product, the momentary product at this particular instant. So this is a behavioral source, and if I now run it, here is what I get. This is the input. You see it's a shifted sinusoidal waveform. The 0 is around 3 volt because I've added 3 volt to it. The output, this is here, is sometimes voltage of forward voltage of a diode. Sometimes it's the full voltage because the diode is blocking it when the sign is minus. Here it is, minus C, and here is the conduction of the diode. And this is now each minute, each instant, the product of the current, I'm not showing the current here, and the voltage, okay? So this is a behavioral model, a behavioral source, and that you can do many things with it. Now, I'm now going to discuss the more general case of a behavioral model in connection with AC simulation when you have more than one variable and you'd like to run AC simulation. Here I ran transient, time domain, but suppose you'd like to run AC simulation. So the first question to ask is, what is the meaning of linearization in a multidimensional function? Now we talked about the diode, which has voltage and current. It's two variables. Voltage is a function, or the current is a function of the voltage. And we said that for that we take the derivative and at the operating point. So the equation now, the small signal equation, will be the small signal, say this will be like the current, small signal voltage, and this is actually the conductance because the other way around, okay? So this is a one-dimensional function, two-dimensional you might say, like the diode. But what if you have a function of many variables, like x, y, z? The definition of linearization is the partial derivative of this function, okay? So the small signal here is equal to the partial derivative of this function with respect to the first one times the small signal x with respect to y, small signal y, and same thing for z. Now, after doing that, this, and this are constant. So therefore, it becomes a linear system. There is no multiplication between variables. This is a variable times a constant, a variable times a constant. So now it is a linear configuration around the operating point. To demonstrate it a little bit better, here is just a graphical representation. Here is the function. Here are the inputs, or the variables. This is the output. After linearization, it becomes this thing. Addition of three sources, you might say. Excitation is the small signal x, small signal y, small signal z, and the output is the small signal u. Just before I'm continuing, for the ones who are wondering, why do we need it? Well, what are we going to do with it? Okay, in behavioral model, average models of PWM converters, we use these configuration or these models. And if we want to run them for AC analysis, we have to understand what is really happening when you run an AC analysis. This again is done by SPICE automatically. That is, if you define in SPICE a source like this, SPICE knows how to take the partial derivative. It's doing it numerically by deltas, okay? But it is generating now a circuit, you might say, which is linear, which is the partial derivative of this. So what did I do here? This is the function. And I have here v sub x. This is the v of x, v of y square. I just put it multiply here, just rather than to the power of 2, Vy squared, and Vz. Each one of them has a DC, an AC. The only small signal is in the Y. Okay? Not adding the other ones, because then the question of phases, etc. So let's not worry about that. So this is the function. Okay? This is the function. Now, since only here we have the excitation, Y hat, small signal, okay? Only this one has it. So I have just to take the derivative, the partial derivative with respect to the Y, okay? This will be 2 Vy times Vx times Vz. This is 5, Vx is 5 volt DC. This is the operating point. Vy is 2. I'm sorry. This should be Vz. Okay, I'm going to correct it. Okay, now it is corrected. So Vz is 2. So if you do this calculation, you come up with 60. That is the gain of this thing when the input is actually this input, the small signal input here. The gain of the whole thing here to here is 60. And if I run AC analysis, in this case I did a linear sweep, doesn't matter because there's no frequency dependence in this case, I see that this is 60. Okay, very neat. Okay, so SPICE is very clever. It can do this linearization of a multi-dimensional function. Now this is very useful when developing average behavioral models of switch mode power converters, and as I have said, if you look up my YouTube channel, you'll find a number of videos on this subject, and you'll see that this behavioral models play a major role there. And since we have this capability of SPICE to do delinearization, it can run both the large signal, transient, and also the AC analysis. It's called small signal because it is correct for a signal around the operating point. But while running it, you can use a large signal, as I've explained. Okay, so a small signal is because it is for the real system, it's valid only for the small excitation, but you can run it in the AC analysis with large excitation, knowing that, of course, the excitation should be small if you like to maintain the linear behavior. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.